That contradiction created a strange new category of computer, technically capable, electrically alive, but officially outside the Windows future. For owners of older Xeon towers, the question was no longer whether the machine could compute, it was whether software would permit it. Rufus became the famous answer, but Rufus was never the deeper story. The real story lived inside Windows setup itself. Because the TPM barrier was not a wall built into the laws of silicon, much of it was an eligibility decision enforced during installation. And once users learned where that decision was being made, decommissioned workstations began returning to service. But there was a catch. Bypassing a compatibility check does not magically make unsupported hardware supported, secure, or immortal. It simply exposes a difficult truth. A policy boundary can exist far above the actual physical limits of a computer. That difference matters when the machine being discarded is not a cheap office box, but a heavy enterprise workstation built to survive years of load. Think of the classic dual-socket tower. Oversized power supply, server-grade board, ECC memory, multiple storage bays, and Xeon processors designed for sustained work. A decade later, its single-threaded speed may look ordinary, but its memory capacity, expansion, reliability features, and core count can still be useful. For rendering, transcoding, simulation, compiling, virtualization, archival processing, and batch jobs, raw age does not automatically mean uselessness. The problem is that Windows 11 judges more than raw performance. Its official requirements include TPM 2.0, secure boot capability, and a supported processor. Microsoft did not invent those requirements merely to annoy enthusiasts. TPM 2.0 is part of a security architecture built around hardware-backed trust. It can protect encryption keys, credentials, Windows Hello secrets, and measured boot information from attacks that are harder to stop with software alone. Secure boot adds another layer by allowing the platform to verify trusted code during startup before the operating system fully takes control. Microsoft also tied its supported CPU lists to reliability, modern driver models, virtualization-based security, and a more consistent security baseline. That is the official logic, and it is not imaginary. The controversy begins where that logic meets hardware that is capable in practice but excluded by policy. A Xeon E5 workstation may support UEFI, virtualization extensions, ECC memory, and enormous I/O, yet still fail the Windows 11 processor list. Another workstation may have a perfectly usable processor, but lack an enabled TPM 2.0 module because the motherboard predates widespread deployment. The installer reduces those differences to a simple verdict: compatible or incompatible. The owner sees only the red line. This is where Rufus became culturally important. It transformed a messy collection of installation workarounds into a few accessible options. Create Windows Media, enable the requirement removal choices, boot the machine, and the setup environment can be persuaded to proceed. But the famous checkbox is only an interface. Underneath it lies the more revealing mechanism, Windows. Setup performs compatibility appraisal before committing to installation. During a clean install, specific checks can be relaxed by configuration changes in the setup environment, including values associated with the lab config path. Users discovered that checks for TPM, secure boot, memory, and other conditions could be bypassed during setup by changing those installer time decisions. That is not a modification of the Windows kernel itself. It is a modification of the conditions under which setup agrees to deploy Windows. The distinction is crucial. Once installed, Windows still runs on the actual processor, firmware, chipset, storage controller, and instruction set physically present. No registry value can create a missing CPU instruction. No setup trick can manufacture firmware functionality that the platform truly lacks. That is why the phrase bypass the TPM requirement can be technically correct while still being dangerously incomplete. There are soft barriers and hard barriers. Soft barriers are policy checks that setup may be told to ignore. Hard barriers are capabilities the operating system actually needs. As Windows 11 evolved, this distinction became more visible. Newer releases began depending on processor instructions, such as POP-CNT and SSE4-2. Those are not branding labels. They are instructions the CPU either executes or it does not. A registry edit cannot emulate them at full system level. Fortunately for many Xeon workstation owners, large numbers of processors from the Sandy Bridge, Ivy Bridge, Haswell, and later eras already include those instructions. So a machine can remain unofficial according to Microsoft's supported CPU list while still possessing the instruction set needed to boot current Windows releases. This is why unsupported does not always mean incapable, but it also explains why bypassing eligibility can never guarantee indefinite compatibility. Eventually, operating systems move upward. Drivers disappear, instruction sets change, firmware assumptions harden, security features become dependencies instead of options. The bypass therefore buys time, not immortality. And for sustainable computing, time can be extraordinarily valuable. A workstation already manufactured has already consumed steel, aluminum, copper, silicon, plastics, shipping energy, factory energy, and human labor. Throwing it away because of an installer gate creates a different kind of inefficiency. Replacing embodied capability before its technical usefulness is exhausted. The global e-waste problem makes that uncomfortable. In 2022, the world generated roughly 62 million tons of electronic waste. Only a little more than 1/5 of that mass was documented as formally collected and recycled through environmentally sound systems. Computers are only one slice of that total, but the principle is the same. Extending useful service can delay disposal and reduce demand for replacement hardware. Still, reuse is not automatically greener. An old dual Xeon workstation can draw far more electricity than a modern system delivering equivalent performance. That matters especially for high-duty cycle computing. A machine running 24 hours a day turns inefficiency into a permanent operating cost. Modern processors have advanced dramatically in performance per watt, idle efficiency, memory efficiency, and specialized acceleration. For some workloads, one recent workstation can replace several older Xeon boxes while using less energy and finishing the same job faster. So sustainable high-performance computing cannot be reduced to old hardware good, new hardware bad. The calculation depends on workload, utilization, and power source. If the machine already exists and is used intermittently for tasks that exploit its strengths, extending its life can make excellent sense. If it spends every night burning hundreds of watts to perform work, a modern system could finish with a fraction of the energy. The sustainability case weakens. This is where careful owners separate emotional attachment from engineering. They benchmark the workload instead of worshiping the specification sheet. A decommissioned Xeon tower might have 16, 24, or more physical cores, but core count alone says little about useful throughput. Some rendering engines scale beautifully across old cores. Some code compilers benefit. Some scientific workloads are limited by memory bandwidth, vector instructions, or cache behavior. Other tasks depend on modern AVX extensions, fast single-thread performance, GPUs, neural accelerators, or storage throughput the old platform cannot provide. The sustainable approach is to assign the old machine jobs it can still do efficiently rather than pretending it remains universally competitive. That may mean CPU rendering overnight when electricity is cheap, running virtual machines in a lab, compiling large projects, or processing archival media. It may mean using the workstation as a secondary node rather than the center of the entire operation. It can also mean abandoning Windows entirely. That possibility is often missing from the conversation because the drama focuses on bypassing Windows 11. Linux distributions can run extremely well on older Xeon hardware, especially for headless compute, containers, development, rendering, and server workloads. If a user requires Windows-specific software, drivers, Adobe applications, proprietary engineering tools, or certain enterprise workflows, Windows 11 may still be necessary. But digital sovereignty is not measured by how cleverly someone forces one operating system to accept them. It is measured by whether they retain viable choices. The most powerful strategy is therefore not a single bypass. It is preserving the ability to move among supported Windows, unsupported Windows, Linux, virtualization, and remote workloads. That flexibility changes the economics of obsolescence. A workstation is no longer worthless because one vendor's compatibility matrix says no. It becomes a pool of CPU cores, RAM, storage, PCIe lanes, networking, and physical durability that can be matched to another role. This was always the hidden value of enterprise hardware. Workstations were designed for environments where replacement costs and downtime mattered. ECC memory catches certain memory errors. Large chassis improve serviceability. High-end power delivery supports sustained loads. Multiple slots permit specialized cards. Those advantages do not disappear on the day a consumer operating system changes its requirements, but neither do the risks. Running Windows 11 on unsupported hardware means stepping outside Microsoft's supported configuration. Microsoft explicitly warns that such systems may experience compatibility problems and are not guaranteed the same support or update entitlement as eligible devices. In practice, many unsupported machines have continued receiving updates, sometimes for long periods. That history tempts users to treat updates as guaranteed. They are not. A feature update can change appraisal rules. A servicing change can reopen a hardware check. A driver can stop working. A future Windows release can add a hard instruction requirement that no registry entry can neutralize. The machine can still function, but the migration path narrows. This is why a responsible bypass begins with backups, not bravado. A workstation performing valuable work should never depend on one unsupported boot volume. The safer design keeps reproducible installers, offline copies of drivers, system images, project backups, and a documented recovery path. If the workstation is part of a compute pipeline, the job definition should be portable enough to move elsewhere when the hardware finally reaches a real limit. Containers, virtual machines, scripted environments, package manifests, and version-controlled configuration can turn a fragile old tower into a replaceable compute node. That is a much stronger form of sovereignty than a permanent fight with one installer check. The TPM question itself also deserves more nuance. Removing the installation requirement does not necessarily mean every TPM-dependent feature disappears. Some unsupported systems actually have TPM 2.0 available in firmware, but disabled, misconfigured, or hidden behind BIOS terminology. Before bypassing anything, the rational move is to inspect the platform. A firmware update or security setting may make the system compliant without any workaround. Other systems support TPM 1.2, but not 2.0. Still, others have a header for a discrete TPM module that may no longer be practical to source, and some truly lack the necessary TPM implementation. Those machines can still run Windows through unsupported paths, but their security posture is different. BitLocker can operate in configurations that do not rely on a TPM, but convenience and automatic key protection can change. Windows, hello, credential protection, measured boot, and other security features may behave differently depending on the available hardware and configuration. A user bypassing TPM therefore should not tell themselves that TPM was meaningless. The more accurate conclusion is that TPM is valuable, but not identical to computational capability. This is the philosophical center of the entire conflict. Security requirements answer one question, performance answers another, support policy answers a third. Microsoft tried to unify those questions into a single Windows 11 eligibility boundary because a consistent baseline is easier to secure, test, and support. Enthusiasts break that boundary apart again. They ask whether a machine can run the code, whether its security is acceptable, and whether the risk is manageable. On a personal workstation, that may be a rational choice. Inside a regulated business, medical environment, defense contractor, or audited enterprise, it may be unacceptable. Support status has operational value. Compliance frameworks, cyber insurance, vendor contracts, and incident response procedures can care more about supported configuration than benchmark results. That means the same Xeon tower can be a brilliant home rendering node and a terrible choice for a production endpoint holding sensitive corporate data. Sustainable computing is not just keeping hardware alive. It is keeping hardware useful without creating larger costs somewhere else. The best repurposing plans therefore reduce responsibility. Old workstations can be isolated, segmented, and assign tasks that do not require privileged access to critical networks. They can render frames, transcode video, compile software, run simulations, host test environments, or process data that is already backed up elsewhere. The machine becomes infrastructure with a narrow job rather than a trusted endpoint that controls everything. That model also makes unsupported Windows easier to justify. If the operating system fails after an update, the workload can move and the node can be rebuilt. The same logic is common in serious computing environments. Individual machines are expected to fail, but the system is designed to survive their failure. There is another reason older Xeons remain interesting. Their original market positioned them differently from ordinary desktop CPUs. Workstation platforms often expose more memory channels, greater memory capacity, additional PCIe connectivity, and features aimed at long-running professional workloads. A modern low-power desktop may destroy an old Xeon in single-threaded benchmarks while still offering fewer slots or less inexpensive memory expansion. For memory-heavy experiments, storage labs, multi-GPU tinkering, virtualization, and unusual PCIe hardware, old workstations can remain uniquely economical. The secondary market amplifies that advantage. Hardware that once cost thousands can become available for a fraction of its launch price after corporate refresh cycles. That price collapse creates an opportunity and a trap. It makes enormous compute capacity accessible, but it hides the electricity bill and maintenance burden. A cheap dual-socket chassis with 2 bargain Xeons can look irresistible until the owner measures idle draw, fan noise, heat, and annual energy consumption. The sustainable decision requires total cost, not purchase price. Sometimes the greenest choice is to use the old system. Sometimes it is to retire it. The important point is that the operating system should not make that environmental and economic decision by itself. A TPM check cannot know whether the workstation is used 2 hours per week, powered by rooftop solar, or replacing a new machine that would need to be manufactured. A supported CPU list cannot see whether the owner needs 8 PCIe devices, half a terabyte of inexpensive ECC memory, or a legacy hardware interface. Compatibility matrices are optimized for mass support. Reuse decisions are local engineering problems. This is why registry-level installation bypasses became symbolic. They restored the owner's ability to make the local decision, even if they did not remove the consequences. The mechanism is almost anticlimactic compared with the politics surrounding it. During setup, Windows checks hardware eligibility before proceeding. By changing setup configuration, replacing or circumventing appraisal behavior, or using media prepared by tools such as Rufus, those checks can sometimes be relaxed. Then, the same Windows image that refused to install can boot and operate on the workstation because the runtime code never depended on the rejected label in the first place. But this should not be confused with defeating a cryptographic security boundary inside the running operating system. The bypass does not crack TPM encryption, forge secure boot keys, or rewrite the Xeon microarchitecture. It changes installation eligibility. That accuracy matters, because dramatic language can obscure the real achievement. The power is not hacking the kernel. The power is understanding where policy is enforced. Once that boundary is visible, users can distinguish vendor choice from physical necessity. And that distinction is becoming more important as software life cycles shorten relative to the mechanical life of professional hardware. Windows 10's end of free support intensified the issue because many otherwise functional machines suddenly required a decision. Remain on an aging operating system, pay for extended support where available, install Windows 11 through an unsupported path, switch operating systems, or replace the machine. None of those choices is universally correct. The best answer depends on security exposure, application requirements, budget, electricity, and tolerance for maintenance. For a workstation that must run Windows-only engineering software, an unsupported Windows 11 install may buy valuable additional years. For an internet-facing machine containing sensitive credentials, the security and support compromises may outweigh the financial savings. For a compute node whose work can move to Linux, bypassing Windows may solve the wrong problem entirely. The deeper lesson is that sustainable computing requires separating the hardware lifecycle from the operating system lifecycle. A computer can outlive the software environment it's shipped with. That does not mean it must become waste. It can be reassigned. It can be isolated. It can become a server, a lab node, a rendering box, a backup target, or a training environment. And when Windows is genuinely required, an installation bypass can be one tool among several, not an ideology. There's also a practical ceiling to how far this strategy can go. Newer Windows releases increasingly assume newer processor features. Windows 11's later generations track CPU capabilities such as POP-CNT and SSE 4.2 during compatibility appraisal, and current releases rely on those instructions for installation and boot. That is the moment when the soft wall becomes a hard wall. If the processor lacks an instruction the operating system executes, setup policy is no longer the only problem. This is why extend hardware life cycles indefinitely cannot be literal. No general-purpose platform remains compatible with evolving software forever. The stronger claim is more defensible and more interesting. A workstation's useful life should end when its real limitations dominate, not merely when a removable setup gate appears. That shifts the owner's mindset from forced replacement to measured retirement. Measure performance per watt. Measure reliability. Measure driver availability. Measure security exposure. Measure the cost of downtime and the value of the workload. If the numbers still work, keep the machine working. If they do not, migrate deliberately instead of reacting to a red compatibility screen. The irony is that enterprise computing already understands this philosophy. Data centers constantly evaluate total cost, energy reliability, and workload placement. They do not retire every server because one application changes its preferred configuration. They move workloads and extract value until economics or risk says stop. Applying that discipline to Xeon Workstations turns a consumer upgrade fight into an infrastructure decision. A tower rejected by Windows 11 can still be a capable tool, but capability must be demonstrated workload by workload. That is the difference between nostalgia and sustainable engineering. The practical reality becomes clearer when we follow what happens during installation. Windows pre-installation environment starts first, loads storage and input drivers, reads the target disk, and launches setup. Before Windows is committed to the machine, compatibility components inventory the processor, firmware mode, memory, TPM state, and other characteristics. The refusal, therefore, arrives before the operating system has demonstrated whether it can actually execute the intended workload. The timing is why setup time overrides work. A lab config value such as bypass TPM check does not teach Windows how to speak to non-existent hardware. It tells the installer not to stop on that particular test. Similar mechanisms have been used for secure boot and other checks. Tools automate the process because automation reduces mistakes, but the underlying idea is simply to alter appraisal behavior before deployment. There is an important difference between a clean installation and an in-place feature upgrade. Rufus itself has documented cases where media prepared to bypass requirements works when booted for a clean install, but does not automatically bypass every check when setup is launched from an existing Windows installation. Microsoft can change those pathways independently, which is why a method that worked for one release may fail on the next. That instability is not evidence that the workstation suddenly lost computational ability. It is evidence that the servicing path changed. Windows setup, Windows update, and feature update appraisers are moving targets. Anyone keeping an unsupported workstation alive has to treat upgradability as a variable, not an entitlement. A successful installation in 1 year says nothing certain about the next major release. The processor list creates another source of confusion. Microsoft's supported Intel catalog includes many Xeon families, especially newer Xeon E, Xeon D, Xeon W, and scalable platforms. The conflict is not Windows 11 versus Xeon in general. It is older Xeon generations and specific models falling outside the validated support boundary, even when they remain powerful enough for useful work. Some older Xeons are especially attractive because depreciation was brutal. Corporations replace workstations on fixed schedules for warranty, standardization, and support reasons, not because every processor has reached physical exhaustion. When those systems enter secondary markets, buyers can acquire large memory capacities and many cores at prices that would have been impossible when the machines were new. But the bargain is only real if the machine's hidden costs are understood. Server-class fans, multiple memory channels, chipsets, discrete GPUs, and dual processors consume power even when the workload is light. Replacement fans, proprietary power supplies, aging SSDs, and rare motherboard parts can also turn a cheap purchase into an expensive dependency. Sustainable reuse is a systems problem, not a benchmark screenshot. Security must be calculated with the same discipline. If TPM is absent, the owner can compensate in some areas with strong passwords, full disk encryption configured appropriately, limited local privileges, network segmentation, and careful backup strategy. Those controls are useful, but they are not identical substitutes for a hardware root of trust. A bypass changes the decision boundary. It does not erase the security architecture that motivated it. The same applies to secure boot. Disabling or bypassing the requirement may allow installation, yet boot chain verification still has value against certain classes of pre-OS tampering. On a disconnected rendering node, the threat model may be relatively narrow. On a laptop carrying credentials across airports and hotel networks, the calculation is completely different. Context decides whether the trade is sensible. This is why the most defensible reuse projects begin with role definition. What exactly will this workstation do? What data will it hold? Will it browse the public web? Will users sign into sensitive accounts? Can the workload be rebuilt elsewhere in an afternoon? The answers determine whether unsupported Windows is a practical engineering compromise or an unnecessary security liability. There's also a performance illusion hidden in the phrase high-performance computing. True HPC is not simply a lot of old cores. Modern scientific software can depend on vector width, memory bandwidth, GPU acceleration, fast interconnects, and highly optimized libraries. An old Xeon Workstation can be high performance relative to its cost for selected workloads without competing with contemporary HPC nodes on absolute efficiency or throughput. And the scale of the broader hardware problem keeps growing. Global e-waste generation is projected to rise further this decade, while formal recycling continues to lag. Recycling is necessary, but reuse sits earlier in the hierarchy. The machine remains a machine rather than becoming a stream of recovered materials. The most efficient recycler cannot recover the original manufacturing energy, assembly, logistics, and functional integration exactly as they existed. The registry bypass, the Rufus checkbox, the clean install trick, these are temporary instruments. The real asset is technical agency. Agency means understanding why Microsoft wants TPM 2.0 and secure boot, while still deciding whether those requirements match the role of a particular machine. It means recognizing that unsupported software carries risk without pretending the hardware has instantly become useless. It means refusing both extremes, blind obedience to replacement cycles and blind denial of genuine security or efficiency improvements. The mature position is harder because it requires measurement, backups, testing, and contingency plans. But that effort is exactly what transforms abandoned enterprise hardware into dependable secondary compute. The old Xeon Workstation does not need to impersonate a brand new PC. It needs a job that matches what it still does well. If Windows 11 is required for that job, the eligibility barrier may be bypassed today. If tomorrow's release introduces a true hardware dependency, the workload moves again. Nothing about that process is indefinite. Everything about it is intentional. And that returns us to the machines stranded after Windows 10 support ended. Towers with spinning fans, healthy memory, working storage, and no official upgrade path. Their value was never determined by one compatibility dialog. The dialogue only determined whether Microsoft would support the next step. Rufus made the workaround famous, but the deeper lesson survives even when Rufus changes, registry methods change, or Windows changes again. Software policy can accelerate obsolescence, but it does not define the final useful moment of hardware. That moment should be decided by security, efficiency, reliability, and the work the machine can still perform. A Xeon Workstation is truly obsolete only when its real limits finally cost more than the value it can still create.